Hey there, everybody. Thank you for joining us for Chemistry Essentials. We'll go ahead and let folks start coming into the Zoom room now. And now is a great time to fill up your water bottles, get comfortable. We have an awesome presentation coming up. I'll hand it off to our presenter here in just a moment. But as folks are coming into the Zoom room, do go ahead and navigate to the bottom of your Zoom window. You should see what looks like a little chat bubble and click that chat. I will go ahead and make sure that everyone can talk. So when you click on that chat bubble, make sure you're set to everyone, and then let me know if you have joined us for a webinar before. And I tell you to set it to everyone just because as you're putting questions in the chat box throughout the webinar, we want to make sure that everyone can see that so they know what Nus is kind of talking about. So go ahead and make sure you're set to everyone, and then let me know if you've joined us for a webinar before. And we'll pass it off to our presenters here in just a moment, but if anyone's grabbing a water or anything like that, that's perfect. Oop, and it looks like we have a few folks returning. Kevin, great to see you again. Julia, wonderful to have you back. Clifford, you too. That's awesome. So we have some seasoned webinar pros here. Awesome. Oh, great. It looks like this is Chris's first webinar, Kathy's first. What an awesome mix. Thank you so much for joining us. And I do just want to make the most of our time together today. So we might have a few folks coming into the room as we're talking, but I do just want to hop into some housekeeping items before we get started. Let's see. News, could you go to the next slide?
Oh, sure. Sorry, I fell
Sorry
asleep.
about that. Yeah, no worries. Let's see. Is the housekeeping items on the next slide,
Oh,
maybe?
I don't know if I created a housekeeping
Oh,
slide.
heck, no
Sorry.
worries. Oh, that's okay.
Sorry.
That's all right. Really, what I just want to let you all know is that you will get a recording of this webinar today. So we're going to both the webinar as well as any resources that we talk about today. I'm going to drop a link to that folder in the chat as soon as I'm done talking here, but you will have access to everything once we have it uploaded and ready to go. The second thing I want to tell you is we would love to answer your questions during today's webinar. It's not meant to be a speech, it's meant to be interactive. So if you have a question, please let us know in that chat box at the bottom of your Zoom window. Make sure that you are set to everyone can receive your chats, and we will try to answer you. If you don't hear from us, feel free to email us. We'd love to help you. And with that, I will pass you off to our amazing presenters. Thank you again for joining us.
Hi, everybody. My name is Nüsret Hisim. I'm a chemistry specialist here at Vernier, and we are going to talk a little bit about what we think are really important sensors and experiments that people do with Vernier equipment. Let me yeah, small amount of housekeeping that I do. This we're going to concentrate on these three sensors today, and we didn't choose temperature because it's one of those sensors that's just wonderful, and there's many experiments, but these three have their own little quirks and questions that come up. Melissa and I are tech support specialists in chemistry, and we answer questions about these sensors all the time. So that's why we chose these three. We are going to mix this up a little bit too. We want to give a little love to the LabQuest people. We want to give a little love to people that have wired sensors. You know, how can I use mine with the latest software? So with that's our plan. I keep mentioning Melissa's name. Melissa, you want to say anything about yourself?
Sure. Hi, everyone. I'm also one of the chemists here at Vernier. I've been at the company now for almost 14 years. And before that, I taught at the college level. I will be doing support. So anytime you put a question in chat today, I'll be quickly answering that. But I'm also here to interrupt Noose with your questions. So definitely put them in chat and I'll interrupt him. I'll keep him on time and make sure that he is answering the questions that we hear a lot from customers about. Because both Nus and I talk to customers a lot. We do a lot of workshops and webinars and go to conferences and things. So we'll be kind of drawing on our experience to tell you the chemistry essentials of those 3 products.
Thanks, Melissa. Yeah, I've known David Vernier since 1984 when I first started interacting with him and the things that he was trying to do, and so I've had a lot of fun with his sensors. I taught chemistry and physics in Maryland for 34 years, and in 2016 I came to the office as a support specialist for chemistry. My job is to do just that, help people out, but also do a little curriculum writing. We've done some lab manuals. One that I've written or been involved with writing 2 frequent, or what am I saying? Recent ones, the food chemistry and the forensic chemistry and lab manuals. And I did include one of those experiments actually in the shared folder that Dylan mentioned a minute ago. So, and love to do training. This is short of being with you. This is kind of one of my favorite things to do. So let's talk a little bit about Vernier and chemistry. There are a lot of sensors here that you can use for teaching chemistry. These here are some of them. You can make an argument for maybe a GC or something. In the forensic book, I put a simple gas chromatograph experiment. So, there's a lot of sensors here, but what are the ones that you're likely going to use the most? Well, probably temperature, right? You have to agree that that's like, but it's relatively simple sensor. And so we thought we would go with ones that, yeah, we get a lot of calls about, for example, pH. We get a lot of calls about pH sensors. So many things like, oh, my students lost the storage solution. What do I do about that? Or, the bulb is broken on the end of my sensor. Can I get it fixed? No, sorry, you can't. But there's some alternatives. I'm going to show you in just a minute. Maryland is humid in the summertime, and when those things are sitting there in the storage closet, they grow mold. I don't know what it is. You come in the fall and they're black. It's okay. It doesn't hurt the sensor, but it's kind of ugly. And my students would have to, wash out the bottles and replace the storage solution. So, one thing you got to have on hand is buffers, especially if you're going to calibrate the sensors or the storage solution is actually a pH 4 buffer. Roughly, it's got some potassium chloride in it. Don't use distilled water. If you lose your storage solution, don't use distilled water. It's better to put some salt water in there or some vinegar or something temporarily until you can get that storage solution put back together. And we sell it. We give you the recipe to make it. These little buffer capsules are wonderful for making the pH buffers. What about how old is your sensor? Well, that's another thing. Vernier warranties sensors, almost every sensor, for 5 years. There's a few exceptions, but generally speaking, even the pH sensors are warranted for 5 years, not counting the bulb. The glass bulb doesn't count, but if you break that, sorry. But the rest of the sensor, if the bulb isn't broken, we expect you to get 5 years out of it. How long can you keep using it? If you can get good data out of it, you can keep going. I mean, 8 years, 10 years. Once you start getting up to that point, though, you got to start thinking about, maybe I need to be, this sensor just is not going to hold hydrogen ions on the bulb as well, or it's got a reference electrode inside that's just getting older and older. And so, you're going to have to think about changing it. Let me bring up a camera here because we're going to do we're going to do 3 experiments, and let me bring a camera up so you can see my setup here. And so this first experiment, I guess I should probably advance the slide. What happened? There we go. We're going to do a titration, right? I mean, aren't you going to do a titration with your students? My guess is you are. And so, but just to make it amusing, I'm going to use the wired sensor, right? This one, I think I've had this one ever since I came to Vernier. So it's a good 7, 8 years old. Okay, and we'll check it out here. You could of course do the experiment with the go direct sensor. Let me get it set up and I'll talk about it while I'm setting it up. I'm going to do a real quick and dirty titration, so I want to apologize to folks. It's not going to be wonderful, but it'll get you the idea. Couple of things we talked about, that storage solution. How do I maintain that? Well, I kept a bowl of nickels in my demo table for years. I didn't worry about the students, stealing the nickels. If you put a nickel over the top of the bottle and then put the cap back on, when your students dump the bottle, you're not going to lose the storage solution. Okay, so get some nickels and have them handy. As far as the bulb goes, mentioned that a second ago. On this style pH probe, the one that where everything is all in one, when that bulb breaks, you now have a Harry Potter wand. You can start casting spells, but there's not much else we can do about it. Okay, so be aware of that. If it breaks, now there's many options for pH probes that come in two pieces. Many. The new one, the Go Direct sensor, is one example of that. There's a BNC connector that separates the electrode from the amplifier, whereas it's all one piece over here. So you can buy the electrodes separately, whether you break it or whether it just gets old, right? So it is possible to replace that where it's not possible to replace it on this sensor. So the other thing we need to do is let's check it. I mean, customer calls and their sensor is not working. What do I do? Well, with this sensor, what I need to do is it's got this white plug. We call that a BTA. It's an analog plug, so it's the A stands for analog. So that needs to get adapted somehow so we can plug it into a computer or a Chromebook. You can also plug it straight into a LabQuest. We're going to do that later with another sensor. Any LabQuest interface, I've got a whole array of them here. I've got a mini and a stream and a LabQuest 2 and a lab. Even the original LabQuest would work for what I'm about to do. I'm going to use the mini because it's the one we recommend a lot of people switch to, especially if you're an old-time Logger Pro user with a Lab Pro interface. It has 3 analog ports and 2 digital ports. So this interface will cover everything that you're likely to want to do with your wired sensors. I'm going to go ahead and plug it in. Notice I'm not being careful. It's in channel 2. Every LabQuest, every single one came with a USB cable. And so you might have to scrounge around if you don't know where those are hiding in your department. But what I'm going to do is I'm going to take this USB cable. And if you look on your LabQuest, there is a USB port. Okay, so I'm going to connect that. Okay, this is a mini USB, and some of the newer ones use a micro USB. This end is going to connect to the computer or Chromebook to the USB port. Let me get graphical analysis up here on the screen. It should theoretically, there we go. So start up graphical analysis, take the USB plug from the LabQuest, plug it into the computer or Chromebook, and let's see, magically delicious, look at that. It just knows, okay, that it's there. So that's kind of nice. I'm going to make a big meter here. Graphical analysis, you can turn on all kinds of stuff. I'm going to turn on a big meter so you guys can see it better. Common question, is my probe working? Well, I don't know. Plug it in, put it into a buffer. Let's find out. So we make, on that first slide you saw, we have all these little buffer capsules that make 100 milliliters. Each capsule makes 100 milliliters of 4, 7, and 10. Pretty common buffers. And there's 10 capsules per bottle. So, that's a fair amount. So when I'm training, I like to put them in these little bottles. Let's check it out. Let me go all the way to the extreme. I'm going to put it into pH 10. So when a customer calls, the question is what's going on with my sensor? And I'd say, well, I don't know. Let's check the calibration. So plug it in. And so let me give that a good whoosh. Now, full disclosure, I did recalibrate this sensor. Now, this sensor, like I said, it's at least 5 years old. It might be older because I think I got it when I came here. But you can see it's doing something there. Pretty good on the 10 end. Let's see how it is on the 4 end. So let me rinse that sucker off a little bit here. So when you're doing troubleshooting on your sensors, buffer solutions are real handy, right? You need to kind of get yourself some buffer solutions. Do you have to use Vernier buffer solutions? No. Flynn ones are fine, Thermo Fisher ones are fine, Hawk ones are, it doesn't matter. But having a nice solution where the what the pH is going to be. I'm going to put it back in the 4. Let's give it a little whoosh. All right, quit fooling around with it. Let's see how it does. If it gets within a tenth or a half of a pH unit or something, well, not a half, a tenth or better, I usually consider that pretty good. And so now think about this too. You're doing a titration. In 99% of well, I don't want to say 99%, but in a lot of titrations, the goal is the equivalence point, the volume of the titrant at the equivalence point. Do you care about the pH? No. So if your probe is off a little bit, you can titrate just fine. Your equivalence point, the volume is going to be at the same spot. The pH might be a little higher, a little low. You're doing, I don't know, diprotic acid or something, and you want to get the Ka1 or Ka2, and you're doing a half titration. Yeah, the pH needs to be good. You need to have a good pH probe for that experiment. But for so many just straight up titrations, or if you're doing an experiment where you're just comparing household acids and bases, who cares if the pH is off by a small amount? It's not going to make much difference at all. So, all right, we're going to titrate an acid and a base. So what I'm going to do is I'm going to, this burette that's you can barely see, but it's not important that you see the top of the burette. I'm going to, let's see, make sure the stopcock is closed. Let me put some sodium hydroxide in there. And if I'm careful, I won't make a huge mess here. If I'm uncareful, I'll go over the top and make a mess. All right, let me see, a little extra dabble there, and I'll bump out the bubbles if I can. Using a plastic burette, still it's not too bad. I got like one bubble that's just gonna fight, so I'm gonna leave it there. All right, let's get this thing up. I don't know. You can do any volume you want, but for our purposes today, I'm gonna do a quick and dirty titration. And so I'm going to start at 0 just to make my life easier. Okay, so that guy's ready. Let's get the acid ready. So, okay, so this would be, depending on your class, this might be an unknown. Okay, don't tell anybody. All right, what I'm going to do, just to make it go quickly, is I'm only going to do 3 milliliters. Just so you guys can get the point. I mean, this might be what we might suggest you do with your students if they just need to get an idea of the equivalence point. Now, we recommend in our experiments 10 milliliters. You could do 5. I've never done a serious titration. Okay, I need a pipette here. I'm just talking and I'm not getting this anywhere near where I want it. So let me grab a pipette and see if I can pull some out here. It's too far down. Okay. So if the students have no idea where the equivalence point is going to be, then you might do something like what I'm about to do. So, ooh, that's so close. I'm going to call it good. It's 3.3-ish, but that's good enough for us. Let me put that in there. All right. The other thing that might concern your students is what I'm about to do, right? I'm going to take some distilled water and I'm going to, I don't know, call it topping it up. But what I'm going to do is I want the whole bulb of the electrode underwater. So I'm going to put under the solution. So I'm going to put, Mr. Hisim, aren't we changing the concentration of the acid? Yes, Mr. And then I would go back and say something like, well, are we changing the number of moles of the acid? Okay. And so that's really what we're after, right? Okay, here we go. Gonna turn this around. Now, the other thing that we need to do is we need to adjust the graphical analysis, because whenever you connect a sensor, it automatically defaults to time. That's true for most of our sensors. So if we're doing a titration, time's not useful for us. We want volume. So on the software, you would tap on the mode button at the bottom. By the way, all these instructions are in the experiment I shared. So don't just watch. You're going to get a copy of these instructions. Here's the time-based screen. This is where you would change things that are time-based. We're going to do that later on. We're doing a gas law kinetics thing in a few minutes. And so I'm going to change it to events with entry. And this is where I can tell it any event I want. In this case, the event will be volume of the titrant. But, there's all kinds of experiments where you might want to use some other thing besides time. And you'll notice that now I have a button next to the collect key. It says keep. Sort of lost my meter, and I really like having the meter, so I'm going to go put that back up again. Well, I just like it. I don't know if it's old school. I use Logger Pro for years. It's so nice to have that meter at the bottom corner there. So we're ready to go. Let me go ahead and collect. And with events with entry data collection, the software waits until the cows come home. It's just waiting on you. So let's not put anything in. I'm just going to hit keep, and it's going to say, well, how much have you added? Nothing, 0. Let's put that in. Got a nice point on the graph. Here's what I'm going to do. Quick and dirty, 0.5 milliliter increments. Okay. So let me pay attention to what I'm doing here. So there's a 0.5 milliliter. Now we want, with titrations, don't go crazy if you're using a stirrer, but you want it to be stirring pretty good, because that pH probe is a slow responder. And so you want it to, have the best opportunity to respond. So spin that up a little fast, not till it's splashing liquid out, but all right, here we go. Another 0.5 milliliter. So I've got 1 in there. Give that pH a chance to stabilize. I'm going to push it a little bit tonight because I have 3 experiments I want to do. And in order to squeeze those in an hour, I'm going to have to push this a little, especially when we get to the equivalence point. You'll see what I'm talking about here in a second. So I'm at 1.5. Let's go ahead and add in another increment. So that's 2 milliliters right there. Watching that pH. Hit keep, so that's 2 milliliters. Let's do 2.5. So if the students have no idea where the endpoint is, then this would be a way to kind of estimate. What did I do? I'm talking 2.5. Okay. And you can see it's starting to take on that characteristic of that S curve, that we all want to see. So let's see. It looks like it's still not bad. What I'm concerned about, of course, is when I get close to the equivalence point, which I think I am very close to right now. All right, 3.5, watching that. Oh, look at that pH. So this is where, we're getting close to the equivalence point. I can't hit keep right now. I want to wait until this thing stabilizes. So we're probably getting past the equivalence point. And that's a good. I mean, we know then the equivalence point must be around here somewhere. And so I'm going to give it a chance to stabilize, and then the next point is going to shoot up like crazy. But you get the idea of how this is working. I think I put about 3.3 milliliters of HCl, and so 3.5 NaOH, and all my solutions here, unless I really need them to be good, usually about 1 significant figure. So this isn't horrible. I normally would wait a little longer, but I want to do some more experiments. So I'm going to go ahead and keep that. What is this, 3.5? And I think the next one's really going to shoot it up there. So let's do that. All right. And then there you go. Watch that pH go crazy. And so what we're going to do in here is not just do the titration, but also, how do you find the equivalence point? And I have 3 different ways using graphical analysis to share with you on how you can find the equivalence point, from a very simple way, depending on the level of your students, the simple way may be all you need, to a little more complex method. And the cool thing is that in the free version of graphical analysis, you can do what I'm about to do. Okay, so that sounds pretty good. Let me keep that one, and I'm at 4 milliliters. I want that classic curve. I want two more increments here just to get that classic curve. And so there's 4.5. You can see now that I'm kind of way past the equivalence point, it's changing very little. Let's get one more point in there just so that it looks like something, the students would recognize. 5 milliliters, give it a second to equilibrate or stabilize, and we'll call it good. And I'm going to stop there. Okay, so now, Melissa, how's it going with questions and stuff? Everything all right?
Yep, we haven't had too many questions yet, but
Okay.
everything's
Load us up, folks. That's why we're here.
Yep.
So we know the equivalence point is somewhere in here. So what we could, with this lousy data, we know is the equivalence point is somewhere between 3 and 4. Right? That's all we know. But if we were doing the same volume of HCl, again, once the pH got to around 3, students would then slow down and put in 1 drop or 2 drops at a time, so you can get a lot more data points in there. You'll get a much prettier looking graph. But you get the idea. This is a quick way. I mean, what did that take? 5 minutes? A quick way to get to this point. With graphical analysis, it's very possible to go deeper into how to get the actual equivalence point. If I take the first derivative, so we have an S curve right here. So if we find, how the curve is changing, and the first derivative kind of tells us that, I can click on the 3 dots next to pH, and I can calculate a first derivative. And like I said, this is built into the free version of graphical analysis. You don't need Pro to do this. Sarah's first derivative is one of my choices for calculations. Let's take a look at that curve. Now, I don't expect a lot, but maybe we'll see. Cross my fingers. Let's put that up there. So that point is close. Remember, that's an actual data point. So it may not be there. It's probably somewhere in between these two. So how can you find the exact point? Take the second derivative, and what you're doing is finding out how this thing changes at its peak. More data points would be nicer, but that's all right. It should give us something okay. So let's take the second derivative of the pH. So do I have to send this out to Excel? You can if you want, but you don't need to. You can do it right there in the software with the free version. Let's take a look at the second derivative. Ooh, look at that. So if I had enough points, this would actually be more impressive. But let me go ahead and highlight that section. More points, like I said, would be nice. I'm going to do a curve fit on this part here where the graph is switching across the x-axis, right? So I'm just going to highlight the data around that. Like I said, more data would be better. And I'm going to do a quick curve fit on that. And let me get this out of the way because one way to solve it would be to set y equal to 0 and solve for x with the slope and the y-intercept. But don't tell your students if you want them to do it that way. Built into graphical analysis is an interpolation calculator. So you can turn that on and you can go in there and you can say, okay, what's the volume right where it crosses the x-axis? So that's where the graph of the first derivative is changing the most. 3.69, like I said, that's what happens when you do a quick and dirty titration. You kind of get in the ballpark, but you would get, a much better value. Nice thing about the software is when the students are ready to create a report, oh my gosh, you can go crazy. You can have all 3 graphs on the screen. You could have the original titration data. Let me turn that statistics off there because we don't need that linear fit there. We could have the first derivative data and the second derivative data. I mean, it's graphical analysis. If I was in the classroom, right? I was in the classroom for a long time and, logger pro. But look at that. I mean, it's just nice, right? Take a screenshot, export it. There's all kinds of options built into graphical analysis to make reports. So it's a nice piece of software. So are there any last second questions before I switch? I know I'm giving you the bum's rush here, but I only got half hour left and I want to do 2 more experiments.
Just go ahead and show the file menu, save and export. But
Sure.
yeah, we got to move on to the other sensors.
Yeah, so you can save the file. If the kids are using a Chromebook, they can stick it on their Google Drive and get it at home. Software is free, or there's other options. It will create PNG files for graphs, so you can save those, or you can put them up, copy them to the clipboard. There's the CSV if you really want to take it out to Excel or Sheets. So lots of options built in. What's not there? Print. Think about that, folks. This software runs on anything. And so we just can't support every possible way you can print, but we can support PNG because it's standard. All right, I'm sorry to give you the bum to rush, but I'm going to quit graphical analysis because I'm going to do something different. And best way to do it is to start with a fresh copy of graphical analysis. So let me get that back up here. One thing I did, which I didn't tell you, is there's a nice presenter view in graphical analysis where I can make things look a little bit bigger. So 3 dots over here. I can go to the preferences and I can zoom things up. So if you're doing a presentation for your students or something like that, that's a real nice thing. All right, I'm going to disconnect the pH probe and go back to that first menu on graphical analysis. So we'll be ready to go with our next sensor, maybe. Didn't like the fact that I did that in the middle of everything. The computer was being a little so like, what did you just do to me? All right, so what I'm going to do, let me go back over here to the presentation. We're going to do a gas pressure experiment, but once again, we don't want to do the most obvious experiment. So we were thinking it would be kind of fun to do something that a lot of people may not think about, and that is a kinetics experiment with a pressure sensor. And what better to do than elephant toothpaste, right? I mean, we're not going to put any soap in it, so don't get too excited. But it is the basics of that. So if I was in the classroom, I would definitely do elephant toothpaste after this. But let me clean up some space here so I can get this next setup. This next setup has a decent amount of stuff here. And we're going to talk about gas laws and all kinds of fun stuff. So let me get all the toys out here. This one we're going to do with the Go Direct pressure sensor, just because that's the new one, and a lot of people are thinking about getting that. It could be done with the wired pressure sensor, and I brought one out. Let me get some things straight and cleared up here a little bit. I'll share it all with you. All right. So let me get myself together here. We'll talk about this in a minute. Put that over here. So here's the Go Direct. Oh, I don't have the camera. Oh, here we go. Here is the Go Direct pressure sensor. This experiment could absolutely be done with the wired, but we have to go through the some kind of interface or something like that. So we thought it would be fun to do one. Try to mix it up. We hit the older sensor there. We used a LabQuest as an interface. This time we're going to do a little bit newer setup. And then the last one we're going to do all in the LabQuest. So hang on to your hats for that one. So what kind of experiments can you do? Well, you can do gas laws, of course, and we'll talk a little more about gas laws in a bit. You can do molar volume of a gas. You can do kinetics, which a lot of people may not realize that you can do the kinetics. And there's a bunch of experiments that you can do with gas pressure sensor. So let me get the kinetics one going. It takes a little while. It's a 5-minute run. So we'll get that going, and then we'll talk more about other stuff. And what I'm going to use for this is I got some fresh peroxide. I just bought it a couple of days ago, and 0.5 molar solution of Ki. And what's nice about this one is that it's a rates experiment. It's not a inverse or a logarithm to find the order. This one you're going to find the order from a rate table, and I really like that because it's a pretty common thing to do. So what we're going to do is I need to check the instructions because I kind of forgot myself. So it's this one right here. It's not crystal violet. It's this one. And it's from our advanced book. And I just need to check, okay, for the first run here. Here we go. It's 10 milliliters of peroxide, 5 milliliters of Ki. I ran this the other day and I just forgot. So I want to make sure that I'm doing it right here for you guys. Let me get it up here. There we go. All right. So going to put 10 milliliters of peroxide and 45 milliliters of water into the flask. So let me get that going here. Like I said, it's a, well, you know what? I'm going to set up graphical analysis too, because peroxide is going to decompose if I take it out. So let's go ahead and do that. With a go direct sensor, you can connect it two ways. Comes with a micro USB cable. All of them do. So you can plug it into the USB port. But what if you're using something that doesn't have a USB port? Like you can collect with go direct sensors, you can collect on your phone, you can collect on a tablet. I am going to connect to this PC because it's my presentation PC. I'm going to do it by Bluetooth. And so I push the power button and this LED is flashing, indicating that it's sending a signal. On graphical analysis, I tap sensor data collection. It looks out into the world and says, what sensors are there. In your classroom, you might have to pay attention to this ID number because you might have a bunch of these in your classroom. And so that's this number right here. And I just simply tap connect, pardon me. And we're ready. Almost. There's a couple of things we need to adjust. Let me get the pressure up here so you guys can see it. Ooh, why is my meter not showing? That's an interesting thing that should have happened. Oh, did it drop? No, it didn't drop. Well, I'm not seeing the meter down here. Interesting. Oh, I'm not sure what's going on here. I might have found a bug in graphical analysis. It's interesting that I'm not thrilled by this because what I want to make sure is I have a reading and I don't even have the little itty bitty meter down here. So I'm going to quit graphical analysis and start it again because I'm not real thrilled by that. And I want you guys to get a good experience. You're spending your time here with us. And so let's try that again and see if we can figure out what's going on. So there's the gas pressure sensor. What should happen with all these sensors is we should get down here at the bottom. There's a little pressure meter. I'm seeing it now. I wasn't seeing it before, and that was what was concerning me. Let me make it bigger so you guys can see what I'm talking about. So I think we're all right. There it is there. Let me see if I can make a big one so everybody can see. I think it's just nicer. There we go. Okay, that's what I wasn't seeing before, and it was bugging me. The other thing is that by default, this sensor sets up for 900 seconds. Way too much time. So what I'm going to do is I'm going to set it up for a shorter period of time. I tap the mode button. This one we're going to run for 5 minutes, and you really kind of need to let it run for close to that. And we don't need data every second. We can take data every 10 seconds. That's wrong. There we go. And that's good enough. And that'll make a smoother graph. That's part of the reason why we're going to do that. So it should be ready to roll. Now I can mix my chemicals up. Let's go ahead and make this a bit bigger. Okay. So 10 milliliters of peroxide. Okay. And I'll get close and put that in the flask. And then let's add 45 milliliters of water. And I just want to make sure that was 50 milliliters of water. I don't know if it's for our demo tonight, it would really matter, but just want to make sure that the bane of pressure experiments is leaks. So before we connect everything and start collecting data, we just need to be careful that we don't have any leaks. So going to check these connections, make sure this valve is closed, that connection, put it on here. I'm almost ready. Need to get my Ki. My Ki is going to be 5 milliliters. Try to be careful here. All right, and I think we're ready. I just want to make sure I got everything set up. Drop the Ki in. give this a little push, make sure it's seated well, and then start collecting data. So, a couple of things to talk about. Isn't that pretty? It's already starting to oxidize the negative iodide a little bit. So, a couple of things to talk about. When you get a pressure sensor from Vernier, it comes with this little bag of goodies. Don't give this to your students. Okay. It'll never come back to you the way you gave it to them. And there's a lot of good stuff in here that you need for different experiments. Like that tubing was in there. There was another one of those stoppers in there. But there's these little clamps that the biology people use for transpiration. There's another stopper that's for test tubes. There's a little syringe. These things are going to end up in the sink. They're going to end up on the floor. What we did at my school is we took all these bags and we got one of those El Cheapo plastic shoe boxes from Walmart or Target or something. And then we would only pull out what the students needed for the experiment. Because, you know, if you give them this, do we sell this? Of course we do. Do you want to have to buy it? But we sell all the individual parts and we also sell the whole kit. So if for some reason it gets misplaced, it can be replaced. Trying to think of what else comes to mind. Oh, gas loss. That's what, okay. So common thing you want to do with gas pressure sensor is gas loss. Well, the syringe is there for Boyle's law, pressure and volume. Very nice experiment in our, I think we have it in both the regular chem and yeah, we do. We have it in both. In the advanced chem, it's experiment number 30. It's called exploring gas laws. In advanced or regular chemistry, it's experiment 6. And that's just the Boyle's law. But can you do, I had a customer question just the other day. Can you do Charles' law? Can you do Gay-Lussac's law? Absolutely. This is the setup. Let me see if I can move this without disturbing it too much. This is the setup I like to use. It's 2-liter bottles cut off for water baths. And then here's kind of a power tip. Connect your syringe to the little valve here, and then that allows you to lower the flask way down into the water bath. So you can get, you know, the whole flask in there. And then you can do, if you're going to do pressure and temperature, Gay-Lussac's, then, you know, you're going to need a temp probe. And what's neat is with Go Direct sensors, this is true, you can hook up 2 wired sensors, but with Go Direct sensors, you can do this whole experiment wirelessly, right? And it's very slick. I did this one at NSTA a few years ago, I think before COVID. And so my challenge to my students was not only to learn the relationship, but also to get a value for absolute zero, right? That was kind of a side goal, was to see what they could get for absolute zero. I have a data set that I shared with a teacher the other day, and I got down to -4. I think, oh, not -4, 4, -274. That's what it was. So it was actually -270. That would be just off by 1, right? So that would be really close. So this makes a nice setup for doing that, for doing the 3 gas laws, and then 4 actually, because I wrote one for the forensics book that's Avogadro, so it's pressure and number of molecules. That's a fun one because you do different gases in that one, and equal volumes of different gases at the same temperature and pressure have equal number of molecules. So you do like air and carbon dioxide, and you can do whatever gas that you know, like butane or propane or something. We're trying to push people away from wasting helium. So, but yeah, in the forensics book, there's an experiment that's an Avogadro experiment, and there's another one in there that's an ideal gas experiment. So you can do a fair amount. Now, what's going to happen with this is if you look at and I can make that data look a little more impressive by zooming it up here, then it looks a little more impressive. What the students are going to do in this is that they're going to fill out, I guess I had that up there. Let me show it to you. They're going to fill a chart with the initial rates. Now, Little bit, we can talk about the semantics of initial rates, but the first three trials, they just changed the volume of either the peroxide or Ki. The last trial, actually, you put everything in I suggest cold water and do it again, and then you can do a little Arrhenius calculation where you can try to get an activation energy from your data. So it's kind of a neat activity because it has that initial rates or rate comparisons, so you can write a rate expression, but you can also do a little Arrhenius calculation out of it. So what the students would do is, notice it stopped at 300 seconds. I would suggest finding the steep, oh, look at that. I would suggest finding the steepest part of the graph and then being consistent, like this one's like from 150 to 200 seconds. Do a little curve fit action here, and your rate for the linear curve fit's going to be the slope. So in this case, the rate is 0.062 kilopascals per second for this combo. And then they would do it over and over again. I put the sample data in the shared folder so you guys can take a look at all three runs at the same temperature, room temperature, and then you can look at the run that I ran. I think it was at 6 degrees Celsius, and of course, very low rate. But the point of that one was to do the Arrhenius calculation. So any thoughts, questions, concerns before I move on to the last one? I think I can squeeze it in.
Yep. Nope. I think go ahead.
All right.
I've handled most of the questions and
Excellent,
keep
excellent,
going.
excellent. All right. The last one was a colorimeter, but what we wanted to do was give some of you LabQuest folks a little bit of love. And so let me get the camera up here so you can see what I'm doing. Camera, camera, camera. There it is. Okay. So in fact, we're gonna do a LabQuest 2, just cause. Okay. But what we're gonna do, we could plug in. Let me see if I can push some things out of the way here. We could plug in a wired colorimeter. Totally possible. Okay. And that would be the older style. But what about mixing things up like crazy? So here is a wired colorimeter. Not really much difference between these functionally, but the GoDirect one, you could plug it into the USB port. The LabQuest does have a USB port. Or, and this is kind of the fun part, is I can connect the colorimeter straight to the LabQuest. Let me get my LabQuest up here. There's my LabQuest 2. And what I'm going to do is I'm going to push the power button on the colorimeter. And so the colorimeter should have an LED flashing. I don't know if you can see it on the camera, but yeah, there you go. It's a little flash. On the LabQuest, I'm going to go to Sensors and Wireless Device Setup and GoDirect. Now on the computer screen, you're not going to see the next little bit because I don't know. I think it's something to do with the power of the LabQuest. On my LabQuest, I'm seeing GDX-COL number 67. That's the colorimeter that's in front of me. If you get a LabQuest 3, then you can actually see everything in viewer, but unfortunately with the older style LabQuest, that one screen you can't see. I'm not going to go through the whole, every wavelength here to find lambda max, but in the experiment that I shared, and we'll talk more about it in a minute, I actually have the students do that. I'm going to take it, we're going to do blue food color, and we're going to use diluted bleach. Okay, so let me get it going and then we can talk more about details and things like that. So I'm going to open up the chamber here. Want to check and make sure that the colorimeter is calibrated. So I'm putting some distilled water in a cuvette. Every colorimeter, the old or the new, came with 15 of these, making sure that the light is passing through the clear sides. And the object is you want the absorbance to be 0. If it didn't read 0, I would push this cal button right here, but it's doing good. So now what I'm going to do is I'm going to take 10 milliliters of blue food color, and No, take note of the label there. There's a reason for that we're going to talk about in a minute. I'm going to give this a little rinse here. And I specifically wrote the experiment the way I did, so it's more visual for students. And we'll talk about that in a bit while it's running, because it's going to take a couple of minutes to get good data. So there's my blue food color. Let me get my bleach. This is diluted bleach. And you really need to test your bleach, because if it's been sitting around a while, it's
Nüsret,
probably.
it looks like we lost connection to the LabQuest viewers.
Oh, no. Oh. We were having trouble with this earlier, and we thought we had our.
Oh, no, it's back. Never mind.
Oh,
We're
yeah.
good. Go back.
I don't know what's
It
going
just,
on. Okay.
there we go. We're
Yeah,
good.
we were having a tech issue where the LabQuest was dropping off, and we thought we had it fixed. Okay, here we go. I need an empty cuvette right there handy. Let me take the two. So this is the blue food color and the diluted bleach. I'm gonna put it into the beaker, give it a swish, pour it in the cuvette, about 3/4 full. Put it in here. Now, what I want on my LabQuest is I'm watching for the highest absorbance. Looks like I'm there, and I'm going to start collecting data. Now, let's talk about this while it's happening. Okay. Couple of things. When you're doing even crystal violet is true. This is true. You want to make a really strong solution, because when you mix them, right, here's the mixture in the beaker. When you mix them, it's going to dilute that by half. So make that absorbance over 1.5. Okay, now little side notes. Spectral analysis, if you do this on a SpectraViz, maxes out at 1.5. So don't get too much higher if you're going to do this on a SpectraViz. The other thing is the bleach. Don't, I mean, you could try it with straight up bleach, but your graph is going to go straight down. It's going to turn, clear right away. You can see how it's lightening up here. This is a 10-to-1 dilution of Clorox. My suggestion is test it so that you get reasonably good data. Okay, because it's real important. This is a bleach, I think, is a little strong. I like this reaction to go for about 200 seconds. For the sake of our short time together, I made it a little bit too strong. I should have probably diluted that bleach. And the point is, right here where the absorbance says 0.1, once we get below that, I mean, the graph will look really pretty, but when you go to do the analysis, it's going to turn out not to be so great. And so what we suggest is that you take data between 0.1 and 1, and anything outside of that range, when you try to do mathematical analysis on it, you get crummy data. So I'm going to go ahead and stop the LabQuest at this point, because we're way below the 0.1, and this will give us really nice data. Now, on the LabQuest, you can do the whole analysis that you could do anywhere else. So with this type of kinetics experiment, common thing to do would be to look at the inverse and the log to see if the integrated rates, to see if the line comes out linear. And so, because right now with this curve, we know that the reaction between the peroxide and the Ki, wait a minute, I'm mixing up my experiments here. The blue food color and the Ki, and the not Ki, bleach, is not zero order, because this graph is nice and straight. So I can go to the data table and I can make a calculated column. Now, what we're assuming is that the absorbance is directly proportional to the the concentration. Those of you that are purists, I put a copy of a spreadsheet in the shared folder you'll get eventually, and you can change those absorbances to actual concentrations if you want to. Okay, it is possible to do that, but for our purposes, We don't need to do that. So I want logarithm, natural log. There we go. Oh, I lost it. Where'd you go, natural log? So we're going to look at the natural log of the absorbance, although I'm having a hard time this LabQuest might just need to be a little bit work done on it. Let me try that one more time. Oh, oh, that LabQuest is being annoying. So sorry. So sorry. Okay. Let me see if I have any other options. This LabQuest is definitely having a hard time.
Noose, we're almost out of time.
We're almost out of time. Okay, what I will do is I will put in the shared folder. This is the shared folder that I set up for you all. I'll put a sample of data in here so you can look at, if you want, what the first order and second order plots look like. And I apologize, we've been struggling with this LabQuest. I think it might be time for it to get replaced. The Wi-Fi. I mean, I have everything on the LabQuest that we just did, but unfortunately, I can't show it to you as nicely as I want to. So with 5 minutes left, let's talk about a couple of other things. And then if you have, like I said, if you have any questions, throw them at Melissa, or let me show you something here. One thing to be aware of is we have a lot of videos on our website. This program that we did tonight will end up on the website. And so if you go to vernier.com, you can search for videos for anything. This is the one I did, the forensics one I did on titration, actually, but there's a whole lot of videos. So that's one thing to be aware of. The other thing is user manuals. All of our sensors, their user manuals are published on our website. So you can get the instructions on how to calibrate or, that kind of thing right from our website. And then the last is lab manuals. We publish a lot of lab manuals. In chemistry, there's a decent number of them. And so you'll find that this will save you a ton of time. The way Vernier works is you buy one copy for your school or for your department, and then that's a site license, and you get electronic files. You get PDFs and Word files. I taught AP Chem for 25 years, Brown and LeMay, Zumdahl, and I would take questions from the books and put them right into the Vernier experiment, and then save that forever. So when you buy one copy of any lab manual, you get a site license for it. So that will save you a lot of, trying to reinvent wheels and things like that. So be aware of that. Okay, is Dylan still on the call? Oh, one more thing. I'm sorry, I forgot one more thing. You can call us, you can email us, chemistry@vernier.com. You can chat with us. We're most of we have this live chat on our website. So getting in touch with us is pretty easy. So please take advantage of that. Don't get yourself, into something for 2 hours when we could probably help you out. So Dylan, are you still there?
I sure am.
Okay, I heard there was going to be a drawing for a free GoDirect pH probe. Is that true?
That's completely right. And we have entered everyone's names into a random name selector. So I'm going to go ahead and run it. And I will let you know who has won the giveaway.
Oh, I should have left a blank here so I could type the name in. I didn't think of it.
Well, I can tell you now, the winner is Ashley S. So congratulations, Ashley. I see you're still online, so that's awesome. We're so excited. I'm going to shoot you an email with a form to fill out as soon as we're done today. So keep an eye on your inbox and congratulations. Yay.
All right. All right. Well, sorry about the bums rush there. Sorry about the LabQuest 2 being annoying. Melissa and I tested everything on Tuesday, and of course it worked fine. But I will share some data. And folks, thank you for devoting some of your evening time to be with us. I know it's tough, middle of the week. So many of you are teaching. But we look forward to helping you out and look forward to talking with you any way we can. And so once again, have a good evening. And I think I've said everything I need to say tonight. Dylan, is there anything I missed?
That's it. I dropped a link to a survey form that you could fill out if you're interested. So please give us feedback. I'd love to know what you want to see more of, what future webinars you'd like to see. So give us your feedback. We'd love to hear it. And I'll drop it once more. There you go. All right, my friends, thank you so much. And I hope you have an awesome rest of your Thursday, a great Friday, and an amazing weekend. So we'll talk to you soon.
Okay. Bye-bye.
All right, bye.